Okay, so let me introduce myself first. So I'm Catherine Sanchna, a PhD scholar from IIT Madras, working under the guidance of Dr. J. Muralikrishnan, the one of the professors offering the course. So I'll be taking the session every Tuesday between 6 p.m. to 8 p.m. And if you have any doubts, you can feel free to comment. And this session also will be posted on YouTube, so you can feel free to comment in the comment section below or below each video, or you can um, just drop a message, drop question through the NPTEL forum, okay, which is available, okay, whose link will be given by the NPTEL team for you to post questions. So let's begin the session without any further delay. Okay, so this course is on mechanical characterization of bituminous materials, and as sir had mentioned in the lectures, here we will be focusing on the characterization of bituminous materials, mostly binder and which is the smallest scale of the bituminous mixture, the smallest scale of the bituminous mixture. And we'll also be learning how to characterize the bituminous mixture as a whole. So first, how I've planned out this session is, since I cannot cover all the contents of week 1 in this 2-hour session, I will be explaining a few concepts which I feel are important, okay, which I feel need attention. So I'll be concentrating on them. In addition to that, we will be solving previous year's assignment questions. Now you can feel free to stop me in between and ask questions, or you can also ask me at the end of the end of each session. Or and one more thing is, if you feel that you want explanation about any other concept which I have not covered in this lecture, you can ask me that as well. So let's begin the session. Okay, so first, sir would have spoken about the basic tests, which are basic tests on bituminous binder, which will be the ones that have been covered in IS 73, which are penetration, like consistency tests like penetration, softening point, viscosity, like that. And later the lecture would have moved to mixture volumetrics. So this volumetric study, sir would have mentioned that it is all about uh, designing the amount of binder required for the mixture, and not about actually trying to find out how this mixture will perform. So first I thought I will go through the mixture volumetrics, the basics, and then we will move on to the viscoelastic models, which I felt that I will be helping you derive the constitutive equations, so that we can go slowly and we'll be deriving that as well. Now, regarding the mixture volumetrics, first we will start with aggregate, okay. Since this mixture, bituminous mixture, consists of, as we all know, consists of binder, aggregates, and these two combine together to form the mixture. Now, so we'll be seeing about the aggregates, specifically the specific gravity of the aggregates. There will be 3 types of specific gravity, which we will see later. Then we will move on to the specific gravity of the mixture, and also some volumetric terms which are essential in mix design. So first we will begin with the aggregate part. Okay. So as we all know, specific gravity is nothing but a relation between mass and volume of a substance, right? But why are there three types of specific gravity for the same material? Okay. So this raises a question, right? So now if you see, all there are, so I've jotted down three types of specific gravity, which are bulk specific gravity, effective specific gravity, and apparent specific gravity. Now, this all these three specific gravities will have the same mass, because um, each aggregate will have the solid part of it, which will constitute to some mass. Along with it, it will have voids, like openings, which will not constitute to any mass because it is filled with air. So all the three types of specific gravities will have the same mass. So it is nothing but density. Specific gravity is, yeah, specific gravity is density of the substance divided by density of water, right? So to get the density of the substance, we need mass and volume of the substance, and this mass is going to be the same for all the three specific gravities. Where each specific gravity will differ is based on its volume. So what volume you choose to calculate the specific gravity helps you to differentiate between the three types of specific gravities. So first, if we move to bulk specific gravity, so if you take an aggregate, okay, if you take an aggregate particle, it will have the solid portion of it, as well as it will have voids. Now, there are three types of voids which you should notice. One is the voids that are present inside the solid particle itself, okay, inside, not on the surface. If it is in the surface, then water can penetrate through it. If it is in the inside of each solid particle, then water cannot access that void, and these voids are called as impermeable to water voids, or impermeable voids. You can call them as impermeable voids. Okay, so these voids will be included in all the specific gravities, because there is no way that you can eliminate these voids from the picture. There's no way you can calculate the void amount which is present inside the solid particles. So this will be present in all the cases, in all the volumes. Now, moving on to the next set of voids, which will be, so if you see this figure, it makes it clear. So there are, so these voids, okay, this is an entire void. Some of it is filled with bitumen, and some of it is filled with water. Okay, actually, if you remove this bitumen, this entire part is capable of being filled with water. It is the bitumen that cannot penetrate into the portions that has only water, but water can penetrate into the portions which are occupied by bitumen. So what I mean to say is, each each void will have water, will can be entirely occupied by water, whereas if you just try to coat it with bitumen, these voids will cannot be entirely filled with bitumen, but only a small portion of it can be filled with bitumen. So all these voids on the surface are completely permeable to water, but they are only partially permeable to bitumen. So they can be classified into two types, two categories. Like one is voids permeable to water, and voids permeable to asphalt. Okay, the voids in which only water can permeate, and the voids in which only bitumen can permeate. So now there are three types of voids. One is the impermeable voids, which will be included in the entire for all the three cases, and the other two types of voids is voids permeable to water and voids permeable to asphalt. Now, how will you calculate these three specific gravities based on the volumes by excluding or including these voids which I just told you? So I told you mass is the same. Now, how will you find out the volume for each specific gravity? Now, what this bulk specific gravity says is, you should include the entire volume of the aggregate along with the permeable and impermeable voids. Okay, so it should have all the voids, it should include all these voids, which means it should cover the entire volume. Okay, so that constitutes the bulk specific gravity. Now, what is, so this we have heard of, bulk specific gravity everyone has heard of. What is apparent specific gravity? It should not include any of the voids. I told you the voids which are inside, these impermeable voids, have to be included in all the three cases. But these voids which are on the surface, they will be completely excluded. Now, how will you select the volume for this case? It will be only this portion. Okay, so it will be only this portion which I am drawing. Okay, so this will be your volume which will be considered for finding out the apparent specific gravity of aggregate. Now, so this we saw, so this volume is obviously lesser than the volume that has been used to find out the bulk specific gravity, right? Now, what is effective specific gravity? So this has the highest volume compared to the three cases. This has the least volume compared to the three cases, and this effective specific gravity will include the voids which are permeable only to asphalt. So how will this look is, okay, so this volume will include only this portion. Yeah, only this portion. Okay, in which only asphalt can permeate, not water. Sorry, it will constitute only this portion in which only water can permeate and not asphalt. Okay, so this portion is neglected. The portion in which asphalt gets filled is neglected. Now, if you see, this volume is in between the volume which was used for bulk specific gravity and apparent specific gravity. So, if you see, these three specific gravity values are not the same, and they are in a particular order of magnitude. Okay, so since this volume is in the denominator, and since this bulk specific gravity has the most volume, this will have the least specific gravity. Since this has the least volume, this will have the highest specific gravity, and this effective specific gravity will be somewhere in between. Okay, so this is what you have to notice when it comes to aggregate specific gravities, right? Just a second. Yeah, so this is what you have to notice when it comes to aggregate specific gravities. Now moving on to mixture specific gravities. Now if you see, just a second. Yeah. Okay. So if you see the mixture specific gravities, again there are three types of specific gravities, which will be, sorry, again there are two types, which will be bulk specific gravity and maximum specific gravity. Okay, so if you see, just like the phase diagram for soil, a bituminous mixture can also have a phase diagram, except that instead of water, it will have, in soil we have a three-phase diagram constituting of soil solids, water and air, right? But in this case, we will have only asphalt, air and aggregate. So instead of water, we will have asphalt. And this asphalt is divided into two portions, which will be asphalt which gets absorbed onto the surface of the aggregates, okay, which, so we saw asphalt permeable voids and asphalt impermeable voids. So the asphalt which gets absorbed on into the voids, that is called as absorbed asphalt, and the remaining asphalt surrounding the aggregate is called as the effective asphalt content. Why is it called as effective asphalt content? Because it is available for use in the bituminous mixture. The other asphalt gets absorbed onto the um, aggregate surface and is of no use when it comes to mixing and compaction, or holding the aggregates together, right? So the asphalt surrounding this is called as effective asphalt. Now, in the same manner, here you will include, in the case of bulk specific gravity, just as we saw for specific gravity of aggregates, in the case of bulk specific gravity, it will include it will include um, the volume of the aggregates, the volume of air, as well as, that is the volume of voids, as well as the volume of bitumen. Okay, so in these two cases also, the mass will be the same, right? Because the weight of air is 0, but the volume of the mass of asphalt and mass of aggregate is has a valid number. So the mass in both the cases will be 0. The only difference is that the bulk specific gravity will take into account the volume of the air voids, whereas the maximum specific gravity will not take into account the volume of the air voids. Okay. Okay, so in this case, if you see again, the maximum specific gravity, as the name says, it will have maximum value because it excludes the volume of air voids. Okay. Now there are a few other parameters which are used in mixture volumetrics. One is air voids of mix. So it is nothing but the air voids, the percentage of air voids, okay, in terms of volume, okay, in terms of volume of the total mix, okay, percentage of air voids. The next is what we call as voids in mineral aggregates. So if you see the voids in mineral aggregates, it is nothing but, as sir would have said, you add bitumen to the aggregates, compact it, and somehow mysteriously remove the asphalt from the compacted specimen. Okay, the structure just assume that the structure remains intact. Okay, even after removing the bitumen content. Okay, now the voids which are present after removing this bitumen content is called as voids in the mineral admixture. So what does this mean? Let us say I've packed mixture like this, okay, and I've removed the binder content. So now I have to find out the voids in the mixture. So what will it have? It will have only the voids in the mixture, say along with bitumen, how much voids you found out, okay, that along with the effective binder content. You have to keep this in mind. Effective binder content and not the total binder content, because only the effective binder content can be found in the voids, right? So this is voids in the mineral aggregate, okay, between the aggregates. So only the effective binder content will be found in the voids, okay. So that is called as VMA. So if you see mathematically, so in the later slides we will see a question for which the answer will be, it will be voids in the mixture along with air voids in the mixture. Okay, I should say air voids in the mixture along with effective binder content. Now moving on to the next one, which will be voids filled with asphalt. This is nothing but the same as, this is nothing but, now you have found out the voids in the mineral aggregate, right? So in this voids in the mineral aggregate, this will have both air and bitumen now, right? It is supposed to have both air and bitumen. Okay, now you have in this VMA, you have to find out how much percentage of voids is filled with asphalt. So you know the air voids in the mix, that divided by VMA. Okay, VMA minus voids in the, VMA will have air and bitumen. Air voids will have only air. So if you subtract that, you will get the volume of bitumen. That divided by the total VMA will give you the voids filled with asphalt. Okay. So we are not going to get into the equations for this volumetrics, mixture volumetrics. We are just saying what each term represents. Okay. Now I'm not going in an orderly fashion. I'm just going which I thought you should know or see, and also a little important, I've given a little importance to the viscoelastic models, right? So yeah, so let's begin with what, so I want you to see what is called as Deborah number. So what do you mean by Deborah number? Okay, is okay. So now if you see, you first we'll start with bitumen. So bitumen has it is a viscoelastic material. So as we've gone through the lectures, as you've gone through the lectures, it is well known that it is a, by now you would have known that it is a viscoelastic material. But I just wanted to show you one video which was taken by my colleague, okay, for his work, and I just borrowed this video from him. Okay, so I just want you to see this video. Okay, so he has placed a ball of bitumen on a sheet of paper and he has observed it for 2 hours. Okay, this video is under a time lapse. Okay, so you are able to see how it deforms with time. Now, this ball of bitumen, had I stopped my observation at this instant of time, okay, maybe it would have been 10 minutes, okay, as per the original video, as per the original time frame. Okay, I could have concluded that it is a solid. So I just place this ball of bitumen, I place it on the table, I just have a look at it for 10 minutes, then I say that and then I'm able to see that the shape is conserved. So I just assume that it is a solid and then move out of the place. For me, I would have concluded that it is a solid. Now, had I observed this material again, just like he has observed, for a longer duration, right, I'm obviously able to see that it has deformed. Now that I've increased my time of observation, I'm able to see how the material has deformed. Right? I'm able to see how the material has deformed. Now I'm able to say that maybe this material is not solid. It has kind of maybe deformable properties as well, because I'm not applying any load to it, but it is deforming under its own self weight, assuming that the temperature in the surroundings is constant. Okay, let us assume that in this 2-hour time frame the temperature is constant, so the body is deforming under its own weight, right? So in this case, maybe I'm thinking that maybe this body is deformable, and so it is not a solid. So since I've increased my time of observation, I'm concluding that now I've changed my decision from solid to a kind of a deformable body or a fluid-like body. So whenever I do any kind of testing, I have to make the choice of how long should I make the observation so that I can capture the response of the material. So this is an important property for characterizing bitumen, because we all know that it is a viscoelastic material, and so you have to make the choice of what should be your time of observation, right? So if you see, right, so in this video, as you saw, so now there are two times associated with this video. One is the time taken for the material to relax or deform. Okay, had this material, so I told you that I for 10 minutes I observed and it was still holding its shape. Let us say that even after half an hour it is holding its shape. Okay, then after half an hour I would have come back and said, okay, it's still a solid. Okay, but after 1 hour, maybe for or after one day, had it deformed, then I would have concluded that it is a fluid. So it's fluid like. So there are two time frames associated with this experiment. One is the time taken for the material to respond, which we will call it as the time of relaxation or material time, right? The other one is how long am I planning to observe this material, which is called as the experimental time or the time of observation. So these two, when we relate these two time frames, we can conclude whether the material is a solid-like or a fluid-like material. So now, okay, so I'm able to conclude whether my material is a solid-like. I'll be able to conclude whether my material is solid-like or fluid-like material. So this the number which relates these two time frames is called as the Deborah number, which Sir would have explained. And this name comes after the prophetess Deborah, who um, who who made a famous statement called "Mountains flow in the eyes of God." And Sir would have explained that he would have also showed you this pitch drop experiment, in which a very hard material called as the pitch has been put in a funnel, and they are observing how this pitch is deforming over a period of years, right? And the ninth drop, right? So from the time this experiment was started till now, only 9 drops have fallen down, and Sir would have said we are expecting the 10th drop by 2020. So there's still now, it's 2024 now, and still the 10th drop hasn't fallen. And there's a famous, there's a live feed which shows you, um, like when, how this pitch drop experiment is being carried out, or it basically helps you to observe how this experiment is actually being done, since it is a 24 by 7 experiment. Okay, so this, if you take a look at this website, okay, which is the 10th watch website. So basically this experiment is carried out in the University of Queensland. Okay, and so if you just open this link, you will be able to see a live demo of the pitch drop experiment. Okay, so I just wanted to show you this as well. So why am I putting this into picture now? Because our material is viscoelastic, and the choice, and we are claiming that it is viscoelastic based on this Deborah number. So let us say if the material, and sir would have explained, like if all the materials are viscoelastic, even mountains are viscoelastic. Okay, leave mountains. Even steel is viscoelastic. Okay, we consider it as elastic material. Even steel is viscoelastic, right? But maybe the time of observation has to be so long that we choose to ignore the time of observation, and we consider it as a perfectly elastic material. Okay, for time being, maybe perfectly elastic material, which does not, whose response does not depend on time, since this time of observation has to be so long that we chose to ignore the effect of time on the material. Okay, that is how we classify materials as solids or fluids. Now our material has this time of relaxation and time of observation, this ratio somewhere close to 1. That is why we consider this material to have properties of both viscous effects and elastic effects, and consider this as a viscoelastic material. Now, in which case do you think this Deborah number will have will be a solid? So so this Deborah number will be a solid if this Deborah number is high. Okay, greater. It has a higher value. Why? In what cases do you think it will have a higher value? Either the denominator has to be high, right? So if the denominator is high, the time of relaxation is very high. So in the case of viscoelasticity, if the time of relaxation is very high, then the material is a solid like material, right? In case of a fluid like material, the stress immediately relaxes, right? Even when you apply a constant stress, we will go through viscoelasticity later. Even when you apply a constant strain, the stress will relax immediately, right? So in the case of solids, this time relaxation time of the material, or the time for the material to deform, is much longer. So in that case, the Deborah number will be high, for which you can conclude that the material is a solid like or elastic like material. And in what other case can the Deborah number be higher? In the case when the denominator is lower. So if the time of observation is less, say for a steel, had I observed it for 1,000 years, maybe it would have deformed a bit, right? Now, if my time of observation is just 1 year, so if I'm restricting my time of observation, then my possibility is high that for me to call the material to be a solid like or a elastic like material. So in that case, the Deborah number again will be high. Okay, so for solid like materials, the Deborah number has to be high. Now, for fluid-like materials, the Deborah number has to be low. So now in what cases will the Deborah number be low? When the time of relaxation is very less. So in the case of fluids, as I explained earlier, the material, to hold a constant strain, the stress will immediately relax, right? So, or the material, in the case of a fluid-like material, it will immediately deform. So in that case, the Deborah number will be lower, lesser. And in one more case, in which the time of observation is very long, then the possibility is high that your material deforms over that period of time. Say, instead of 1 year, I'm looking at steel for a period of 1,000 years, just as how it would have actually responded, okay, or it would have deformed maybe in 1,000 years, and I'm planning to observe it for over a period of 1,000 years. Now my time of observation is more, and the possibility is high that I can conclude, for me to conclude the material to be a fluid-like material. So in such cases, if the numerator is low or the denominator is high, the Deborah number will be lower. In such cases, I can conclude the experiment. I can conclude Deborah number to be smaller, and in such cases, it will be a fluid-like material. So I just want to show you this website, since I planned this earlier. Okay, Okay, okay. I'll show you this some other time, or you can even go to this website. It will be as per the Queensland timing. Okay, so we have a lot more to complete, so we will proceed. So I just wanted to tell you about this, focus on this or highlight on this Deborah number. Okay, and since I wanted to show you that video, now we'll move on to viscoelasticity, which is the main crux of bituminous materials. Like, because the material is viscoelastic, I wanted to focus on this concept as well. Okay, so let us say, so sir would have explained that viscoelasticity is an additive decomposition of elastic and viscous like properties, but he was careful about saying that it is not exactly addition, but for time being, for simplicity, we will just separate them as two components with elastic and viscous properties. All right, so there are three kinds of tests, or basically two kinds of tests, which from which we can conclude how the material response can be, okay, for a viscoelastic material, by considering the responses of elastic and viscous materials. Okay, so let us say, so actually I told you there are two kinds of tests. One is a time domain test. What do I mean by a time domain test? I perform this experiment over a period of time. Okay, I either do a constant stress experiment, which I will call it as a creep test, or I will do a constant strain experiment. So I will provide a constant stress or constant strain to the material over a period of time. So this constant strain experiment is called as stress relaxation experiment. Now, why I plan to why I plan to do it over a period of time is, so in the case of, okay, this material is a time dependent material, right? So even if I provide a constant stress or a constant strain, the response is not going to be constant with time. Okay, unlike solids. Okay, so let us see this in detail. Okay, let us take two cases. Okay, one is, this is in time domain because I'm observing it over a period of time, right? So in the case of time domain test, okay, let us take two cases. One is a creep test and one is a stress relaxation test. In this case, let us see how an elastic material will respond. Okay, in this case, when the material is subjected to a constant stress, how do you think the material response will be? It will be subjected to a, so the material response will have a constant strain. Why? Because at each instant of time, the stress is the same. So obviously, strain has to be same. Only then the Young's modulus will be constant with time, right? Because the material properties are not going to change with time in the case of an elastic material. Now, in the case of stress relaxation test, right? Now, when I unload this, okay, so this is called as creep, and when I unload it, I will call it as creep and recovery test. So when I unload it, then again the strain will come back to zero. Okay, there will not be any residual strain. This is in the case of an elastic material. Now let us take a stress relaxation experiment. To hold a constant strain, okay, the elastic material has to provide a constant stress. Okay. Now, if I remove this strain, the stress will come to zero. Only then the strain will can be brought down to zero, right? To maintain that strain, I have to provide a constant stress, And if the strain has to be removed, then the stress obviously has to be removed. This is in the case of an elastic material. Now let us consider the case of a viscous material. Okay. In the case of a viscous material, when I do a creep and recovery test, right? So creep is a constant. So elastic material, it actually goes by the formula of Young's modulus. Modulus is equal to stress by strain, right? Now in the case of a viscous material, you know what viscosity is, right? You know what a Newtonian fluid is. It is a Newtonian fluids or viscous materials are characterized by material parameter called viscosity. Just like elastic materials are characterized by material parameter like Young's modulus or modulus, um, viscous materials are characterized by viscosity. So if you see the equation for viscosity, it is nothing but stress by strain rate, right? So a viscous material will have a constant viscosity with time. Okay, we are not going to talk about temperature. Let us assume that at a constant temperature, with time, the viscosity of the material is going to be constant. Now, if I provide a constant stress to this material, then as per this equation here, my strain rate is going to be constant. Why? Because my viscosity is constant. Now, if my strain rate is constant, how do you think my strain should be, right? This is my strain rate and it is constant. My strain then should vary linearly with time, right? Because my strain rate is constant now, not strain. Now, when I remove this load, okay, when I remove this load, my strain rate will go to 0 because my stress is going to 0 and the viscosity is a constant. Whereas this strain will remain as such, which means there will be a residual strain in the material, right? There will be a permanent deformation. So this is in the case of viscous material subjected to a creep and recovery test. Now let us come to a stress relaxation test. So in the case of a stress relaxation test, to provide a constant strain, my material has to be subjected to an infinite stress, okay, to move the material. So to deform the material, my material has to be subjected to an infinite stress. At that momentary infinite stress, why I'm calling it as momentary is because once I provide that stress, okay, and the material has been subjected to the required amount of strain, the material will immediately relax. The stress will immediately relax, okay. It will not stay in the material. Why? Because if you see this figure, it is well known that once you remove that stress, the strain is not going back to 0. It is remaining as such, right? So in the case of a strain control test also, once I bring the material, say I'm elongating it, once I'm bringing it to the required strain, there's no need for me to maintain that stress because this elongation will remain as such since it is a viscous material, right? For example, actually you should not elongate a viscous material. Maybe I'm subjecting it to a shear. Just imagine that I'm subjecting it to a shear, okay? So this strain remains as such. So there is no need for excess stress to be applied to maintain that strain, unlike in the case of elastic materials. So this will be the material response for a viscous material. Now our material is viscoelastic, which means it will have properties of both elastic material and viscous material. The basic assumption, okay, a very rudimentary assumption, okay. So in the case when I'm subjecting, so let us um, take a viscoelastic material and subject it to a constant stress, right? In that case, there will be an instantaneous jump, okay, which is because of elastic response, uh, elastic response in the viscoelastic material. There will be a delayed creep response, okay. So this will be my strain response. Now, when I remove this stress, right? Okay, right. So when I, sorry. Now when I remove the stress, just flip this figure, okay. It has to be like this. There will be an instantaneous recovery, just like there was an instantaneous jump. There will be an instantaneous recovery, and there will be a delayed recovery. So if you see this, it is just a flip of this curve. Why? Because of the principle of superposition, which we will see later, okay. So this is the response of a viscoelastic material when subjected to a constant stress. Now, in the case of constant strain, okay, so what will an elastic material do? It will try to maintain a constant, in the case of constant strain, it will try to maintain a constant stress. A viscous material will have a momentary increase in stress and it will immediately relax. Now, what will a viscoelastic material have? It will have combination of these two, which means it will have some finite amount of stress and it will start to relax, okay. Now based on these values, okay, the values of strain and stress in the case of stress control or strain control experiments, we can conclude whether this viscoelastic material has more viscous like properties or more elastic like properties, right? So it is a combination of, obviously it is a combination of both viscous and elastic um, properties, okay, as per our assumption. Now this combination can either be 50-50 or it can be 80-20 or 20-80, right? But how to conclude whether it is a viscoelastic, it is dominant in elastic properties or dominant in viscous properties? In that case, what you will do is, what you will see is, in the case of a creep test, which is a stress control test, at the end of time t, so after at any time t, after the experiment has, after you remove the stress, if there is a permanent, oh sorry, residual strain in the material, it is a fluid like material. Why? Because a solid like material will try to reach zero, right? The strain will try to recover for a solid like material, whereas in the case of fluid like material, there will be a residual strain in the material even after the stress has been removed. So in that case, we can say that if this is the case, if there's a residual strain in a stress control experiment, you can conclude that this material has a dominance in viscous properties, right? Now moving on to uh, strain controlled experiment. In the case of a strain controlled experiment, okay, after a time t, if this stress goes to zero, then you will say that the material has a dominance in elastic properties. Why am I saying that? Because in the case of a fluid like material, this stress will try to go to zero. It will try to relax, right? Because here, if you see, in the case of viscous, it relaxes immediately. So if it relaxes completely, then it has a dominance in fluid like properties. Whereas if it has some, so the response is stress, right? Whereas if it has some residual stress at the end of time t, then we can say that the material is has dominance in elastic like properties, okay. So if it immediately drops to zero, if it drops to zero at time t, then it is a fluid like material. Whereas if it has a residual stress at time t, then it is a elastic like material, solid like material. So if you see, they are completely opposites. Like if it has residual strain, it is a fluid-like material. If it has residual stress, it is a solid-like material. Okay. So this you have to keep in mind. Now this is in the case of time domain test. Now there's something called as frequency domain test. So what do I mean by frequency domain test? Okay. Now why did we bring into consideration the effect of frequency in viscoelastic materials? If you go through Weinman and Rajagopal, you will see that, say, if you see this material, right? So this material, its response depends on time. So if you have to find out the response of a material, um, or if you have to know the response of a material, you have to wait for a sufficiently longer time in some cases to find out the response of the material. So in order to accelerate the testing procedure, they would have tried to adopt the frequency domain testing. So what do I mean by frequency domain testing? Within a short duration, I'm going to subject the material to various frequencies. I'm going to try subjecting the material to various frequencies and try to examine how the material is going to respond and get the material properties from that experiment and see if I could use it in some kind of um, a design or distress characterization. Okay. So what do I mean by a frequency domain testing? Earlier I said that in the case of time domain testing, the time remains the experiment is carried out over a period of time, either with in the case of constant stress or constant strain. Now in the case of frequency domain test, you apply a sinusoidal loading for a time period of t. Okay, let us say if this time period is 1 second, and if if there's only one sine wave in 1 second, then the frequency of this waveform is 1 hertz, right? So any sine waveform will have amplitude and frequency. Amplitude is this value, and frequency is number of cycles per unit time. If I consider this time to be in terms of seconds, okay, and if there's only one cycle in 1 second, then I will call it as 1 hertz. If there are 10 cycles in 1 second, then I will call the sine wave to have a 10 hertz frequency. So in this manner, I can subject the material to any frequency of sine waveform and with any amplitude. In the case of similar to the time domain test, in the frequency domain test also we can do a strain controlled or stress controlled experiment, and based on the response of the material we can conclude whether the material is solid like or fluid like, right? So here also I told you there are two kinds of tests to conclude whether it is a solid, fluid, or viscous, elastic, or viscoelastic material, right? One is this time domain in which you saw creep and recovery, and one is this now frequency domain. Here also, creep and recovery is nothing but a stress control test. I'm controlling the stress, right? And creep and recovery is a stress control test. Relaxation test is a strain control test. Similar to that, in the case of frequency domain testing also, we have two kinds of tests. One is a strain control test and the other is a stress control test. In both the cases, you will apply this sinusoidal waveform, right? And how will the material response be if the material response is elastic? Okay, let me draw here. If the material response is elastic, then for a sine wave given like this in strain control mode, my stress response will also be a sine waveform of the same frequency. Okay, if this is 1 hertz, this also will be 1 hertz, and it will start at the same time at which this strain starts. Okay. Now in the case of a stress control test for an elastic material, again the response will have the same sorry yeah the response will have the same frequency as that of the input waveform, and it will also start at the same time as the input waveform. Okay, both are starting at time 0. Now um, yeah so now this is in the case of a elastic material. In the case of a viscous material, when I subjected it to a strain control test, my stress response will start ahead. Okay, now you may get confused as to how it will start ahead. When I mean start ahead, it means that at time 0 the stress is not 0. That's all. It does not mean that it has started ahead of the experiment. It just means that at time 0 the stress is not 0. Even when strain is 0, the stress is not 0. Okay, that is what I mean when I say the stress waveform leads. Okay, it starts ahead. That is what I mean. This is in the case of a viscous material. And how much is the difference? Okay, so let us say I'm writing this in terms of radians. Okay, you know that 360 degrees or one full waveform constitute to 2 pi radians, and 180 degrees constitute to pi radians, right? And then 1/4 of the waveform should be pi by 2 radians, right? So this is 90 degrees. Now this stress which leads the strain waveform, it leads by pi by 2 radians, which means when it is 0 here, the stress will be maximum at 0. Okay, when the strain is 0 at time 0, the stress will be maximum at time 0. So this is what I mean when I say that the stress leads. Now let us do it the other way in the stress control test. Okay, in the case of a stress control test, where do you think the strain response will be? Do you think the strain will start ahead just like the stress has started ahead? Okay, it should be noted that always it is the stress which will lead the strain. So no matter you do stress control test or strain control test, the stress waveform should always be ahead of the strain waveform. So if my stress has started here, then my strain should start a bit later. Okay, so this will be my strain response, and how much late it will start? It will start by pi by 2 radians. So when it is 0 at time 0, it is also 0 at time 0. Strain is also 0 at time 0. But when stress is maximum at pi by 2, it is still 0 at time 0 at pi by 2. Okay, at time of pi by 2, and from there only it starts to respond. Okay, so you should always remember that it is the stress which leads and not the strain. Okay, be it in a stress controlled or strain controlled experiment. Now this is for a viscous material. So how should a viscoelastic material be? It should have a combination of elastic and viscous properties, right? So elastic material had a phase lag of 0 degrees. So there was no phase lag, right? When it started at the response started at the same instant of time as that of the input waveform. So there is no lag in the response of the material. Whereas in the case of a viscous material, we saw a lag or lead of pi by 2. Lead of pi by 2 in the case of stress, and a lag of pi by 2, right, in the case of strain. So this delta, which we will call it as phase lag. What is phase lag? The phase lag is the lag in time between the stress and strain the difference in time between the stress and strain response. Okay, so that phase lag is pi by 2 in the case of a viscous material. So in the case of viscoelastic material, this phase lag, okay, delta should be in between 0 to pi by 2. So what do I mean by this? When I give a stress input, my strain output should again lag the stress response, but it should lag by a phase angle somewhere between 0 to pi by 2. Okay, this is in the case of a stress controlled experiment. In the case of a strain controlled experiment, the stress will lead the strain waveform, but it will lag, it will lead by a phase phase lag of 0 to somewhere between 0 to pi by 2. Okay, so this is in the case of a frequency domain testing. Now, why did I do these tests? You know that any material you cannot simply, so if you want to characterize a material, you should associate some material property to it. Only then you will be able to say that, you will be able to put it into some use. Like maybe you can use it in the design. You can, why do I want to characterize a material by its property? Because when I want to use it in a design, I can always ask for the designer or the engineer or someone who's designing that I want a material with this property. So I have to ask, right, that I want these properties in a material. So for that case, I have to qualify or quantify a material based on some property. Okay, now if you see, in the case of an elastic material, how do you think it is characterized? It is characterized by Young's modulus, as I said earlier. So why it is characterized by Young's modulus? Now it is a it is a property. So it can be characterized by stress or strain also, right? Say I'm subjecting it to a subjecting the material um, to 5 megapascal stress. Okay, let us say I'm subjecting it to a, say, 5 Newton load. Okay, let us say I'm pulling a bar by 5 Newton. So I can always ask the manufacturer to say to give me a material which responds to a 5 Newton load by, say, a deformation of 1 millimeter or 1 centimeter. Let us say 1 centimeter. So um, if I ask the manufacturer, just subject this give me a material which deforms by 1 centimeter when I subject it to 5 Newton load, that is not standard, right? It all depends on, it'll depend on the area of cross section. Because if my bar has a larger area, then when I subject it to 5 Newton load, it is not definitely not going to deform by 1 centimeter. Or it will depend on the length of the bar, right? So it is not standard. So I cannot ask a manufacturer based on properties that will keep varying based on the geometry of the material or shape of the material, or geometry or shape of the material. So I need to associate it with a property which is independent of the geometry of the material. That is why they resorted to Young's modulus, right? So no matter what area, so area is nullified. So if you give a 5 Newton stress, 5 Newton force, it is nullified by area to give stress. And if you give 10 centimeter bar, it is nullified by change in length by original length. So it is nullified by this length to give strain, and the ratio of stress to strain will give you Young's modulus, right? So they have associated elastic material to a property called as Young's modulus, which will not depend on the geometry of the material. In the same way, you have to associate your material also to some property so that you can characterize its response. Okay, kind of like that. Now our material, so unlike elastic materials, unlike steel, just imagine steel as your example. Now unlike steel, your material is going to keep varying with time. Okay, so you cannot give a constant value as as your material property. Your material property is not going to be a constant, but it is going to be a function. It is going to be a function of time. Okay, so in that case, you have to find out the material property. So you know that Young's modulus is valid in the linear viscoelastic regime, a linear regime, right? Only when the material response is linear, then you can only then you can call the ratio of stress by strain as Young's modulus, right? Only then it will be constant. Only till the linear limit it is a constant. Similarly, only in the linear viscoelastic regime you can make use of the properties which we are going to define now. Okay. Earlier, I told you that when I subject the material to a constant stress, the viscoelastic response of the material will be like this, right? Strain. Now, when I subject the material to a constant strain, the stress response of the material is going to be like this. Okay. Now, if you see, all the x-axis is time. Now, so this is sigma, right? So if I increase the sigma by 2 times of sigma, and if this strain response also increases by 2 times of epsilon, okay, so this is 2 sigma, then this is 2 times of epsilon, then it means that my material response is scalable. Okay, so no matter what stress or strain I give, okay, similarly here also, if I increase it by 2 times of epsilon, the response will increase by 2 times of sigma. So no matter what is the stress or strain of the material, as long as it is in the linear viscoelastic regime, this shape will be conserved. Okay. So what does this mean? I can always bring these down to one common curve just by nullifying this factor. Okay. So in that case, I can bring all these to one common curve. How can I do that? Just like you found out Young's modulus to be stress by strain, here also you have something called as a stress relaxation modulus or a creep compliance modulus. So what does this mean? I will have a modulus value, and as I told you earlier, its values will vary. It is a function, not a constant. So it will vary with time, but it will have one single function. It is a one single function which can hold for a range of strain values. So this will also have the same shape as that of the stress function sigma of t, but I will divide it by this constant value of epsilon naught. Only then, whenever, so if I increase strain by twice, this stress also will increase by twice. Only then it will get cancelled and G will be the same. So as long as the material response is linear viscoelastic, I can make use of these material properties which are functions of time, unlike elastic materials which are constants, which have constant material properties, right? Similarly, this is for a stress relaxation test. You will call it as a stress relaxation modulus. Similarly, in the case of a creep compliance test, okay, you will call it as, in the case of creep and recovery test, you will call it as a creep compliance function that is also a function of time, and that function is given by epsilon of t divided by sigma. It will have the same shape as that of epsilon, but you are dividing it by the constant stress that you are applying to the material. Okay. Only then it can be, this property can be applied to a wide range of materials as long as the material response is linear. So I kept saying that this is valid only in the linear viscoelastic regime. Why did I say that? So you know that, right? So you know that in the case of Young's modulus, stress by strain curve is a constant. Okay, so this slope is the Young's modulus. Similarly, in the case of a viscoelastic material, I have to subject it to a constant stress, right? And the material will respond like this. Say this is my strain, this is my stress. At each instant of time, so this is say 1 sigma, 2 sigma, 3 sigma, this response will also be 1 epsilon, 2 epsilon and 3 epsilon. Whatever I am multiplying the stress with, the same will get multiplied to strain. Only then these can be brought down to one single curve. Okay. So this property is called as scaling. Okay. If I'm scaling the stress, then my strain also will get scaled. Only then I can represent it by a common property similar to what you saw here. If you increase the stress by a factor, the strain will also get increased by a factor. Okay, increased by a same factor. Only then this modulus, Young's modulus, will remain constant. Okay, so this property is called as scaling. Also, it has to obey one more property called as superposition. So what do I mean superposition? So what do I mean by this? Let us take um, input stress of sigma 1. Okay, okay, let us say I'm taking a material, I'm subjecting it to a stress of 5 newton, 5 pascal, sorry, stress of 5 pascal, and I'm taking the same material, a different sample, and I'm subjecting it to a stress of 10 pascal. Okay, for this, let us say that my strain response is 1%. Okay, now, usually in viscoelasticity, we represent strain by percentage. Okay, so let us say that my strain response, just a second. Okay, so this is my stress of 5 pascal. This is my stress of say 8 pascal. Okay, and this is my stress of 13 pascal. Okay, so I've taken 3 samples, 1, 2 and 3, and I'm subjecting them separately to same material, okay, but 3 different samples. I'm subjecting it to 5 pascal, 1 to 8 pascal and 1 to 13 pascal. Now let us say the response of the material, which is this is stress, right? So let us say that the response of the material at any time t, so time has to be constant, right? We have to compare with constant time, right? Because the material keeps varying with time. So at any time t, let us say my response, my strain response, say it is 1% here. And in the case of sample 2, at time t, it is 1.3%. Then only if my response at time t is 1 plus 1.3%, which is 2.3%, can I call this material to be scalable, superposable? Why? Because 5 plus 8 is 13, right? 5 plus 8 is 13. So the response which the sample undergoes when subjecting it to individual stress, if it is the same, so when I add these two responses, it should be the same when I subject the material after adding these two stresses. So I did a test of 5 pascal, 8 pascal on 2 different samples. Now summation of that is 13 pascal, right? So this 13 pascal, I'm subjecting it to another sample. Now I'm going to check whether the response given by 5 pascal and the response given by 8 pascal, if I add these together, is it the same response which I get when I subject this third sample to 13 pascal? So if this is 2.3%, which is 1 plus 1.3%, then the material response is said to obey superposition. You know that this holds good also for elastic materials like steel with Young's modulus. Okay, so it not only means that um, my material has to obey scaling, your material also has to obey superposition. Okay, only then the material response can be considered to be linear. Okay, so in the case of viscoelastic materials, it can be considered as linear viscoelastic, only it obeys scaling and superposition. Now, why it has to obey scaling and superposition? As I said earlier, they have to be represented by a common material property, like stress relaxation time, or stress relaxation modulus, or creep compliance function. All these are functions. So why do I need these functions now? Say, let us say now I'm doing a test. Okay, I'm doing a test and I'm subjecting my material to 5 pascal stress. Okay, and based on the response, I found out for this material, I know that my response is the material property, which is stress relaxation function. Let us say I'm subjecting it to a constant strain. Okay, when I subject it to a constant strain, I will get a stress relaxation function. When I subject it to a constant stress, I will get a creep compliance function. Now when I do this, okay, so let us say I know the material response, my stress relaxation function I know. Now I'm subjecting it to 1% strain. Okay, I can simply, so G of T is nothing but sigma of T by epsilon naught, right? So epsilon naught I know. This is what I'm subjecting the material to. G of T I somehow found out from this principle of scaling superposition, uh, or by just fitting some time function to the experimental data that I have. Okay, let us assume I have a function, I found out somehow the stress relaxation modulus. Then I can easily find out this how the stress response will be just by multiplying the stress relaxation function with the stress strain response that I'm giving. That is why we need material properties like this. Okay, so this is in the case of a time domain test. Now what will you do in the case of a frequency domain test? Same way. Okay, now here also it is identified by two properties. Okay, each test will have two properties. One is how much phase lag each material will undergo, and what is the ratio of this peak stress to peak strain. So when I subject it to a strain control loading, and let us say that my stress response is like this. Okay, it has a lag of, say, delta. Okay, this is for a 1 hertz data. Okay, 1 hertz frequency, I'm subjecting the material to 1 hertz sine wave of 1 hertz frequency. Okay, with a stress strain of, say, 1%, and my stress response is, say, 5 pascal. I can find out something called as G star of omega, which is nothing but the ratio of peak stress to peak strain. Okay, so it is nothing but 5 divided by 0.01, right? Peak stress to peak strain, 1% is 0.01. So this is called as um, absolute value of a let us for simplicity I'll call it as complex modulus. Okay, as things move on, we can get the terms clearer. For now I will call it as complex modulus. Okay, but it is not a complex number now. What I define now, it is not a complex number. So say it is just sigma naught by epsilon naught. Just as you write Young's modulus as sigma by epsilon, this complex modulus is nothing but ratio of the peak value of stress to the peak value of strain. In the same way, you will have a phase lag. We saw that every material, all the viscoelastic materials will have a phase lag from varying from 0 to pi by 2, right? So that will also um, be a material property. So why am I calling it a material property? As long as the material is in the linear viscoelastic regime, this material property will hold good for a range of stress or strain values. Okay. Only thing is that it will vary with frequency. Okay, as long as it is linear, it will vary only with frequency. If my material response enters into non-linearity, then it will vary with both material like stress or strain, okay, and frequency. Now, so if my response, now if this is for 1 hertz, then if I'm subjecting the material to 10 hertz, it will be some other phase lag and some other complex modulus, okay, not this. And you can predict it in some other way, like using a function. Just like you use a g of t function, you can have a g of omega function, okay, and to find out what will be the material response at different frequencies. But you cannot simply, here it is, frequencies are not scalable, okay. So if my modulus at 1 hertz is, say, 5 megapascal, my modulus at 10 hertz will be something else. It will not be 5 megapascal into 10. So the property of linearity comes in terms only with respect to stress or strain and not frequency, okay. So this has to be kept in mind. So we saw why it is important to characterize a material using some material property, right? Now, so we saw linearity, and just we went through the basic definition, which is it has to obey the principles of scaling and superposition. Now for you know how the material will respond when the material is subjected to a constant stress or constant strain, right? Now, how do you think the material will respond when it is subjected to a function like this? Say I'm subjecting it to a stress like this. How do you think it will respond? You know how it will respond when only when it is subjected to a constant stress or a constant strain, or a sine function, right? But how will the material respond? How do you think you can find out the material response when it is subjected to a stress like this, right? So that is when you will use this Boltzmann superposition principle. As the name says, you just now saw what superposition is, right? You can split one stress as sum of two stresses, right? Say if this is 13 Pascal, and I can sum it up as 5 Pascal and 8 Pascal. The response I can find out just, so if I want to find out the response of 13 Pascal stress when subjecting the material to 13 Pascal stress, and if I have data which I've carried out at 5 Pascal and 8 Pascal, and I can simply add them up, right? In the same way, what you can do is, here also you can apply the principle of superposition. So what you will do is, so I would like to stop here, because I've planned a lot, like viscoelastic models. I've planned all the derivations. If you want the derivations, maybe we can discuss next week also. So before that, I simply would like to, first I would like to solve the previous year's assignment questions, and if time permits, we will come back to Boltzmann superposition principle and the derivation of Maxwell and Kelvin model. Okay, um, we can do that next week also. If you ask, we can do that. Okay, do that next week along with. Um, anyway, sir will be starting with Berger's model, so we will, along with Berger's model, we will solve Maxwell and Kelvin and then proceed to the next week portions. So for now, we will solve the previous year's assignments first. Okay, so yeah, so the first question is, material characterization involves experimental investigation, model development, testing for failure. So in the starting of the class itself, sir would have said why material characterization is required. First, it is used for design, and second, it is used for distress, right? um, so if you see, for design, a contract, when you're designing the pavement, obviously you require properties like modulus. In the case of bituminous pavement, in the for as per IRC you require resilient modulus, right? So what is resilient modulus? It is a material property which is obtained using material characterization. So that you need it for design. So for that involves or you for to characterize a material, obviously you have to perform experiments. Only then from the experiments only you can either develop models and get the material properties, or you can do some analysis and then get the material properties. So it requires obviously experimental investigation, it requires model development, and as I said, it is also used for distress characterization, so testing for failure. So the answer to this will be all the above. Bulk specific gravity of bituminous mixtures include. So uh, in the in the first few slides we saw that bulk specific gravity will include impermeable voids which are inside the soil solids, and permeable voids which are permeable to asphalt and water, which is nothing but voids permeable to water and voids impermeable to water. That's all. Okay, so permeable and impermeable voids normal to the surface. Now the third question is, voids in mineral aggregate is numerically equal to what? So we saw VMA. What is voids in mineral aggregate? It is nothing but mysteriously taking out the binder content after you have compacted the mixture. So it is nothing but the summation of the air voids in the mixture and the effective binder content, which is the binder which is present only in the voids and which is not absorbed onto the surface of the aggregates, and this taken as in terms of volume and not weight. Okay, so you have two options which are very similar. One is air void content plus effective binder content by mass, and the other is air void content plus the effective binder content by volume. So the answer is it is in terms of volume. So moving on to the next question. It is important to understand the characteristic behavior of the bituminous materials to select better material that suits the location, design the pavement, predict the performance, or all the three options. So why do we need material characterization? Obviously to design, then to predict the performance or predict the distresses in the pavement, and select a better material that suits the location. So had you listened to sir's lectures, you would have noticed that sir would have said we do not play much with the thickness of the pavement, because the thickness of the pavement more or less depends on the lift thickness. Okay, so it all depends on the contractor. So what we play around is the choice of the material. So we do to make a proper choice of the material, we need to characterize the material. So select better material that suits the location. So it serves all these three purposes. So the answer is all three of them. Okay, so moving on to the next question. Which of the below characteristic feature distinguish bitumen from other construction materials? Okay, it is very well known that bitumen is a viscoelastic material, which means it has time dependent properties, right? We saw its material function itself, its material property itself is a function of time. So it is a time dependent, as it has time dependent characteristics. Does bitumen have temperature sensitive characteristics? Obviously yes. Okay, because at high temperatures it will have lesser viscosity, at low temperatures it will have higher viscosity, so its properties will vary with temperature as well. I'm telling you with the basic property, but other properties will also obviously vary with temperature. Okay, by other properties I mean material properties also. Okay, so it has temperature sensitive characteristics. And is it crude source dependent? It's crude source dependent chemical composition. So you know very well that or you should have heard about this, that asphalt is obtained from crude oil. Okay, from fractional distillation of crude oil. So what else do we obtain from crude oil? Petrol, diesel, LPG, kerosene, everything is obtained from crude oil, right? So after removing these lighter components, the final heavier portion which is obtained from the crude oil, the last residue is your bitumen. Now this bitumen will also, the chemical composition is very complex because no one, till now no one is able to figure out what exactly is the chemical composition of bitumen. And so and also, since crude oil is obtained from fossil fuels, is from the decomposition of fossil fuels, no one knows the actual chemical composition. And crude oil from one source, say from source A, and you have two crude oils from source A and source B, they will have, or most of the time they will have, completely different chemical composition, completely different mechanical properties. So none other material will depend on the um, source of the material as well. So here, depending on the crude source also, your material properties will vary. Okay, so it is also crude source dependent. So here the answer is all the above. Okay. The temperature during the production of hot mix asphalt mixture is maintained above what? So here there are four options: 120, 100, 150 and 200. So if you go through the manual for mix design, you will see that for unmodified bitumen, the mixing temperature is roughly around 150 degrees Celsius. Now this obviously depends on the type of material. So in every mix design, you have to find out the mixing and compaction temperature using some test. Either it can be using a rotational viscometer test, where you subject the material to a constant shear rate at different temperatures and find out what should be the temperature corresponding to a viscosity of a particular value, or you can do tests in a dynamic shear rheometer. So if you have to meticulously find out the mixing and compaction temperature of bitumen, you have to do it, you have to properly test for the mixing and compaction temperature. But roughly, for an unmodified bitumen, the temperature is close to 150 degrees Celsius. In the case of this is the mixing temperature. If you have a modified bitumen, you can say it will be around 165 degrees Celsius, like 15 degrees more than the unmodified bitumen. But in any case, it has to be found out using any of the tests which I mentioned earlier. Okay. So moving on to the next question, penetration of bitumen is measured at 25 degrees Celsius. So one interesting story about penetration is, so earlier, before this penetration could come into existence, so penetration is just a measure for consistency of bitumen, right? So before penetration could come into existence, people tried to find out the consistency of bitumen by chewing bitumen. So what they actually did is, yeah. So what they actually did is, they used to bite the bitumen, and based on how chewy it is, they found out the consistency. And the the test temperature, when people try to find out the consistency by chewing, will be the body temperature of will be the normal body temperature. Okay, so that is an interesting fact. But this is a very rudimentary method, where one's opinion will the opinion on consistency will depend on from person to person. So it is highly dependent on um, highly subjective. So later they moved on to something called as the penetration test, and initially this test was carried out at 4 degrees Celsius. Later only it was changed to 25 degrees Celsius. So penetration is a very basic test which tells you nothing about the properties of bitumen, except that it is simply a consistency test, where say if you are uh, working in a bitumen production company and you are producing barrels of bitumen. In order to check for the consistency of bitumen across the barrels, you do basic tests like penetration and softening point. Other than this, and other than grading the bitumen, you cannot you cannot determine the performance of a bitumen based on such tests. Okay, but anyway, in any case, these tests are very important because they are very simple and give you some idea about the properties of bitumen, the basic properties of bitumen, but they can never tell you about the performance, about the quality of the bitumen or its performance in the field. Okay, the bulk specific gravity of bituminous mixtures we just now saw this. Then if the total asphalt content of a mixture is 5.2% by weight and the aggregate absorbs 0.4% binder by total mix weight, the effective binder content of this mixture is what? So as I said earlier, effective binder is the binder which is present in between the voids and around the aggregates and not which is absorbed onto the surface. So if I'm adding 5% of bitumen, obviously some will be absorbed by the surface, and that should be excluded when I find out this effective binder content. It is this effective binder content that is of use to the mixtures in mixing or compacting or the performance. Okay, so the total binder, which I said to be 5%, they've added 5.2%, and out of which 0.4% has been absorbed by the aggregates. So what is the effective binder content now? It will be difference between these two, which is 4.8%. Okay. Now moving on to the next question. For the design of bituminous pavement, IRC 37 recommends to use dash. So in IRC 37, if you see, they would have used resilient modulus, like they would have used MR. MR is nothing but resilient modulus. In India, in India, we use resilient modulus. Okay. The response of the bitumen is said to be linear only if the modulus is okay. So we saw the definition for linearity, and when I explained linearity, I told you that even if you change the frequency, the material response will not be scalable as per the frequency. It is considered to be linear only if it is scalable or if it obeys the principle of superposition with respect to the stress magnitude. Okay, so it has to be independent of stress magnitude. So if I give 5 Pascal and 8 Pascal, okay, why am I sticking on to these two numbers? I don't know. Say I'm subjecting it to 5 Pascal and 10 Pascal. If I'm able to represent these two by a one single creep compliance function, then it is independent of stress magnitude, right? Because this has been nullified for this stress effect. So it is considered to be linear only if it is independent of stress magnitude, or it can be independent of strain magnitude. None other than this you can include. It will obviously depend on time, because our property material function itself depends on the time of load application. It will obviously depend on frequency in the case of frequency domain test. Okay, but it will never depend on the stress that I'm applying. Okay, if the material response is linear. Is it independent of temperature? Obviously not, because with decrease in temperature or increase in temperature, material response is going to vary, and it cannot be represented by any common function. Or is it independent of all the three? Obviously no. It is only independent of the stress magnitude, okay, or strain magnitude. Okay. The two common distresses of the pavement that are considered in the design of flexible pavements are, okay, this is a well-known question. We consider only fatigue damage, which is cracking in the pavement due to repeated loading, and rutting, which is longitudinal depression observed along the wheel path of the pavement, right? So we consider only these two distresses in the design of flexible pavement. Okay. Now moving on to the next question. In an elastic material, all the energy is dissipated, no energy is dissipated. Okay, so we did not talk in terms of energy dissipation. So I would like to explain something about energy dissipation, and let me explain with respect to frequency domain test. Okay. Now let us say I subject the material to a stress controlled test. Okay. I'm subjecting it to a sine wave. Now, in the case of an elastic material, the strain will also start at time 0. Okay. Now, if I try to plot a stress and strain curve, it will be a straight line like this. I'm very sorry. It will be a straight line like this. I'm sorry. It should pass through the origin. Okay. It will be a straight line like this. And how do you find out energy dissipation? It is just the area under the stress strain plot. This is only a area within the stress strain plot. So it is only a straight line. There is no area inside this plot, right? So which means the energy dissipated when in the case of an elastic material is 0. It means that all the energy has been stored in the material. Okay, no energy is dissipated or no energy is lost. In the case of a viscous material, same subject. This is in the case of both stress controlled and strain controlled test. Okay, if it is an elastic material, the energy dissipated is 0. In the case of a viscous material, okay, the strain will lag the stress response by a phase lag of pi by 2, right? And in that case, if you draw a stress strain plot, it will look like this, a perfect circle. Okay, if it is pi by 2, it will be a perfect circle, stress strain plot. Now the energy dissipated will be the area under the stress strain plot. All the energy will be dissipated. Whatever energy that has been supplied to the material will be dissipated because it is a viscous material. Now what will happen in the case of a viscoelastic material? Okay, this is stress and this is strain. Okay, so it is not going to be pi by 2 but somewhere in between 0 to pi by 2. Right. So in that case, if I draw a stress strain plot, it will be an ellipse. Okay. Here, some of the energy is lost and some is stored. The stored part of the energy is attributed to the elastic nature of the material, and the dissipated energy is attributed to the viscous nature of the material. So it will be an ellipse. So these plots or the stress strain plots are called as Lissajous plots. Okay. So in the case of viscoelastic material, it will be a perfect ellipse. So all you have to know is, in the case of an elastic material, all the energy is no energy is dissipated. In the case of a viscous material, all the energy is dissipated, and in the case of a viscoelastic material, some energy is stored and some energy is dissipated. Okay. So in the case of a elastic material, no energy is dissipated. Okay. So moving on to the next question. The constitutive relation tau is equals to mu times of epsilon naught, where tau is the shear stress, mu is the viscosity, and epsilon naught is the shear rate. A strain rate describes what? So this is an equation which we saw for dashpot, right? And dashpot is a example for a viscous material. Okay. And what is a viscous material? A Newtonian material is a completely viscous material. I think everyone should be aware of this. So it is not a non-Newtonian material. So if it is a non-Newtonian material, how will this equation look? It will be tau is equals to mu times of epsilon naught into epsilon naught. So this mu will be a function of strain rate. Okay. Whereas in the case of a Newtonian material, this mu will be a constant. So non-Newtonian material is also a viscous material. It can also be a viscous material. Newtonian material can also be a viscous material. But how will you differentiate from this equation whether it is a non-Newtonian or Newtonian material? Newtonian material will have a constant value of viscosity, whereas non-Newtonian material will have a value of viscosity which is will have a function, a viscosity function, and not a constant value. Okay, so here the answer is Newtonian material. Okay, when do we say that the material creeps? So if you so long I've been saying one thing, we creep and recovery test. So what is a creep and recovery test? Creep is when I subject the material to a constant stress. You would have heard of this term in structures as well, where the material will start to creep under its own self weight. It will not be subjected to any load. It is just the dead weight of the material, but over a period of time, for this dead weight, the material will start to deform. So that we call it as creep, right? So whenever a material is subjected to a constant stress, we call it as creep. So among these four options, we know that two options have constant stress. So what will happen under this constant stress? If the material creeps, the strain will increase, which means it will start deforming, right? Only then you call it as the material to creep. You can call the material to creep, right? So the answer to this is when the strain increases for the constant stress, you will say that the material creeps. Okay. Now, which of the below is a characteristic function of viscoelastic material? Okay. So, recovery in the material occurs gradually, obviously, right? We saw that in the case of a creep and recovery test, the response was like this. Okay. So, in the case, the recovery will occur gradually, okay, over a period of time. So, the first option looks good. Now, second option is stress and strain are out of phase with each other by 90 degrees. So, what will be out of phase by 90 degrees? Only a viscous material will be out of phase by 90 degrees. Now, the third question is the net work done is zero and the material is when the material is loaded and unloaded. So, this is not the answer to um, a viscoelastic material. Okay, this comes for, I guess it is for an elastic material. I'm not sure. I will just take a look at it and let you know next week. And all the energy is dissipated. So all the energy will be dissipated in the case of a viscous material, right? So the answer to this is only option A. Now moving on to the next question. In the elastic material, the stress and strain due to sinusoidal loading are out of phase by. So elastic material, what did we see the phase lag to be? It should be 0. For a viscous material, the phase lag should be pi by 2. And for a viscoelastic material, it should be between 0 and pi by 2. Right? So in the case of an elastic material, it is 0 radians. For the case of a viscoelastic material, the phase difference between the stress and strain for sinusoidal shearing is, as I said just now, it should be between 0 and pi by 2 radians. Now, next question is, some material exhibits the quick recovery and some other material exhibits the delayed recovery after loading. Pick the correct order of the material behavior that exhibits increasing recovery time. So, which will have, okay, let us take two materials, a solid and a fluid. So, which will have uh, increased recovery, delayed recovery. I'm subjecting it to a stress and I'm releasing it. Okay. Now the material will be subjected to a strain and it will start recovering. So the strain will go to 0. In the case of a solid, this will recover immediately, right? So first we have to write it in terms of increasing recovery time. So the first material which will immediately recover is an elastic solid. Okay. So which one will recover the least, like which one will have a residual stress always? It is a Newtonian material, right? Because we saw When subjected to a constant stress and on recovery, the strain will keep on increasing, and at the end of recovery, it will remain constant. So it will not recover at all. So in the case of a Newtonian material or a viscous material, so it will have the highest recovery time. So in between, it has to be obviously viscoelastic material, right? Viscoelastic. Now, there are two viscoelastic options which you can see here: viscoelastic solid and viscoelastic fluid. So, which one should come after elastic solid? Obviously, it should be viscoelastic fluid, and after that, it should be viscoelastic solid. Viscoelastic solid here, and after that, it should be viscoelastic fluid, and only then Newtonian. So, if you see the order, an elastic solid will have a strain recovery almost immediately. Viscoelastic solid will have a little decreased strain recovery. Viscoelastic solid will be having a little more decreased strain recovery. It will take even more some time to recover. The strain will take some more time to recover, and Newtonian material will not have strain recovery at all. Okay, so it is this option. Moving on to the next question. When the Deborah number is less than 1, how will the material response be? We saw that Deborah number is relaxation time by observation time, right? And I told you, if this Deborah number is small, then the material response is fluid like. Why? Because when the relaxation time of the material is small, for a fluid like material, the stress will immediately relax, right? So if the relaxation time is small, or if the time of observation is long, so if I look at steel, say for 1,000 years, then I may say that it is a fluid, right? So if my observation time is long or my relaxation time is less, then the material response can be considered to be fluid-like. In both the cases, when the relaxation time is less or if the observation time is more, then the Deborah number will be less, right? So if it is less than 1, it will be a fluid-like material. Moving on to the next question. Upon creep loading and recovery of a viscoelastic fluid material, all strain is recovered. Only part of the strain is recovered. No strain is recovered, leaving a constant strain, or no strain is recovered and the strain keeps increasing. So in the case of creep, so let us say viscoelastic fluid-like material. So catch the word fluid-like. Okay. In the case of a creep loading and recovery, here will all the strain be recovered? If you see the figure, so this is stress and this will be my strain. I'm removing the load. So it will have only this much strain will be recovered. This portion will be not be recovered. So it is a only, so the option is only part of the strain will be recovered. Okay. So moving on to the next question. In a strain control test on a viscoelastic material for a fluid-like response, okay, catch the word strain control test, viscoelastic fluid-like response. So we saw two cases, right? One is a stress control test and one is a strain control test. In the case of a stress control test, how will a fluid-like response be? It will increase, the strain will increase and then it will recover, but it will have a residual stress. Okay, this is for a fluid like material. In the case of a strain control test, the stress will relax and it will go to 0 in the case of a fluid like material. In the case of a solid, it will have a residual stress, right? So here it will be stress relaxes completely. Okay. In a strain controlled oscillatory test on viscoelastic materials, stress response is in phase with the strain response. Stress response is out of phase with the strain response by a phase lag of okay. So now we know that viscoelastic material, so stress and strain will have a phase shift. Okay, we can call it as a shift. So if it is a stress waveform, you will have a shift. And since it is a viscoelastic material, it will neither be 0 nor pi by 2, but it will be between 0 and pi by 2, right? So in that case, now you have two options with, generally they've given delta as the phase lag. Now if you see, here is the catch. Strain response is out of phase with the stress response is out of phase with the stress response by a phase lag, or stress response is out of phase with the strain response by a phase lead. So I told you that whatever be the test, be it a stress controlled or strain controlled test, it is the it is the stress which should always lead. So the answer to this is stress response is out of phase by a phase lead. Okay. Now, these questions, there are 7 questions. These questions were there in this year's assignment as assignment 0. So since they will not be graded, I've added these questions also. In the next sessions, if you have any queries regarding other assignments, but after the deadline, then I will be able to clarify them. I will not be able to clarify any of those questions before the assignment deadline. Okay. Okay. Is bitumen primarily an organic material? So what is an organic material? We would have learnt in organic chemistry that any material with carbon and hydrogen atoms are organic materials. And if you see bitumen has n number of carbon atoms. It has many carbons, many isotopes of carbons. It is a high molecular weight carbon compound. So it is an organic material. Okay. What is the naturally available raw material used in the production of bitumen? So when we saw a few questions back, I told you that bitumen is obtained from crude oil, right? So that is the raw material for bitumen. What is the nature of response exhibited by bitumen under ambient conditions? So bitumen is a viscoelastic material. Okay, but I told you that the response of bitumen varies with temperature, right? So it varies with temperature and rate of loading. So if I take bitumen at say 200 degrees Celsius, no matter what rate of loading you give, it might behave as a completely viscous material. Okay. Now let us say I'm testing bitumen at minus 30 degrees Celsius, okay, below the glass transition temperature. Its glass transition temperature will be around minus 20 degrees Celsius. Let us say I'm testing bitumen at minus 30 degrees Celsius. Then the material can exhibit a purely elastic behavior, okay. Even in such cases, when we see time temperature superposition principle, I will explain how even in minus 30 degrees Celsius also, if I load it at a frequency of say 0.0001 hertz, if it is possible by the equipment, if I'm able to apply very low loading frequency to a material at minus 30 degrees Celsius, it can behave like a viscoelastic material. But let us say, for instance, for neglecting the effect of frequency, let us say for the range of frequencies that can be accessed by my rheometer, by my equipment, okay, if I'm able to test it at minus 30 degrees Celsius, it can exhibit completely elastic behavior. But what is the question here? So you cannot simply say that my material is a viscoelastic material. Okay, all real life materials are viscoelastic. You should keep that in mind, right? Even mountains flow in the eyes of God. So all materials are viscoelastic. But the question here is under ambient conditions. Okay, so even bitumen at high temperatures or very low temperatures, it can be a purely viscous material or a purely elastic material. But under ambient conditions, it will behave as a viscoelastic materials. What do we mean by under ambient conditions? Say room temperature. Room temperature, it is obviously a viscoelastic material. So the answer to this is viscoelastic. Okay. Moving on to the final set of slides. Okay, final slide. What type of distress occurs in pavement due to repeated loading? We saw this a few questions back. It is fatigue cracking. And what type of distress is characterized by longitudinal depressions formed in the wheel parts of the pavement? That also we saw. It is rutting, right? And this question we already saw. It is resilient modulus. And the stiffness of bitumen generally increases with decrease in temperature. So what we saw in the earlier slide, at high temperatures it will behave. It has a high possibility of behaving as a viscous material, which means its stiffness will be very less. At low temperatures, it will behave like an elastic material, which means its stiffness will be very high. So its response depends on temperature, and it actually increases with decrease in temperature. So it is true. Okay. So if you have any questions, you can ask now.
Yes, ma'am, Catherine, ma'am.
Yeah.
Yeah, I just have a question. I mean, this regarding the test, like the linear amplitude sweep test and all,
Mm.
it will be later towards the later part of the lectures and all, right?
Was it mentioned in the syllabus that they will include linear amplitude sweep?
Well, I haven't gone through the syllabus.
I
Is there a
have.
syllabus
I
as such?
Sorry.
Is there a syllabus as such under course content? I'm not sure.
I'm not sure about that, but I have access to lectures all the 12 weeks. So maybe I will take a look at it and I will let you know next week, ma'am.
Okay. So
Yeah.
when will the next, I mean, this interactive session be? I mean,
Every Tuesday between 6 to 8 p.m.
okay, every Tuesday between 6 and 8. Okay, okay, okay. Okay. Thank you. Thank you.